In the next four examples, we will describe the various reactors needed to produce 200 million pounds per year of ethylene glycol from a feedstock of ethane. We begin by finding the rate constant K for the hydrolysis of ethylene oxide to form ethylene glycol. Example 1. Determine K from batch data. It is decided to design a CSTR to produce 200 million pounds of ethylene glycol per year by hydrolyzing ethylene oxide. However, before the design can be carried out, it is necessary to perform and analyze a batch reactor experiment to determine the specific reaction rate K. Because the reaction will be carried out at temperature contact, the specific reaction rate will need to be determined only at the reaction temperature of the CSTR. At high temperatures, there is a significant byproduct formation, while at temperature below 40 degrees centigrade, the reaction does not proceed at a significant rate. Consequently, a temperature of 55 degrees centigrade has been chosen. Because the water is usually present in excess, its concentration might be constant during the course of the reaction, and the reaction is first ordered in ethylene oxide. So here we have ethylene oxide plus water gives us ethylene glycol in the presence of sulfuric acid. Schematically, we can say A plus B gives us C, where A is ethylene oxide, B is water, and C is ethylene glycol. In the laboratory experiment, 500 milliliters of a 2 molar solution, which means 2 mole kilograms per cubic meters or 2 moles per liter of ethylene oxide in water was mixed with 500 milliliters of water containing 0.9 weight% of sulfuric acid, which is the catalysis. The temperature was maintained at 55 degrees centigrade. The concentration of ethylene glycol was recorded as a function of time. See table E4/1.1. And using the data in this table, determine the specific reaction rate at 55 centigrades. So here we have the data of the lab time against concentration of ethylene glycol, which is the product. So we are going to use this data later on here. So analysis. Problem statement. Determine the specific reaction rate K. So the sketch is a batch reactor. Identify relevant theories. Mole balance for the batch reactor. DNA divided by dt equals Ra times B. And the rate law minus Ra equals Ka times Ca to the first power because it's first order, the reaction. The variables, the dependent concentration of Ca, Cb, and Cc, independent time, knowns and unknowns. We know the concentration of ethylene glycol as a function of time. Unknowns, we don't know the concentration of ethylene oxide as a function of time, Ca. The specific reaction rate, Ka, we don't know either, and the reactor volume, we don't know. Inputs and outputs, reactant fed all at once to a batch reactor. Missing information? None. Does not appear that other source need to be sought. Assumptions? Well, is a batch well mixed, all reactants enter at the same time, no side reactions, negligible filling time, isothermal operation. Approximation? Water is in excess so that its concentration is essentially constant, Cv equal to Cv0. Specification? The problem is neither overspecified nor underspecified. We have all we need. Solution. Here is where it comes the algorithm. First, we start with the mole balance on a batch reactor that is well mixed, and we know that for a batch reactor, the mole balance is 1 divided by the volume B times dNA divided by dt is equal to Ra, the rate, and from the rate law, minus Ra equal K, the concentration of A because it's first order, and because water is present in such excess, the concentration of water at any time t is virtually the same as the initial concentration, and the rate law is independent of the concentration of the water, and the concentration of the water is Cb equals Cb0. From the stoichiometry, we are in a liquid phase, no volume change, and here we have the stoichiometric table. In the species, we have ethylene oxide, water, and ethylene glycol, the symbols A, B, and C. For ethylene oxide, initially we have Na0, the change minus Na0 times X, what is going to be consumed. What remains is Na, which is equal to Na0 times 1 minus X, and going to concentration divided by the volume is going to be concentration Ca equal to Ca0 times 1 minus X. For water, at the initial, we have for water theta B Na0, where theta B is Nb0 divided by Na0. The change is minus Na0 times X, because in the reaction they are 1 to 1. And the concentration of B is going to be Cb equals Ch0 times theta B minus X. And for C, the concentration of C is going to be Ch0 times X, because Nc is equal Na0 times X. They are in a relation 1 to 1. From here, the concentration of A, we say, which is Na divided by B, is equal to Na divided by B0, and is so from the expression of the mole balance, we will have 1 divided by B0 dNA divided by dt is going to be the Na divided by B0, but this is the concentration, so it's going to be dCA divided by dt, and that's the rate. And combining the rate and the mole balance, we will have that minus dCA dt equal to kCA. Minus dCA dt comes from the mole balance, and K times Ca comes from the rate law. So minus dCA dt divided by dt equal kCA. So we evaluate for isothermal operation in this way. K is constant, so we separate variables and integrate the equation. So we will have that minus dCA divided by Ca is equal to K dt. The integral of dCA in Ca is natural log of Ca, and the limits from Ca0 to Ca then will be natural log of Ca divided by Ca0. But to take the negative number, we will put natural log of Ca0 divided by Ca. So using the initial condition that when the time T is equal to 0, then Ca equal to Ca0. The initial concentration of A after mixing the two volumes together is 1 mole per liter because we had two samples of 500 milliliters and we mixed it, so the concentration got half. We had 2 moles per liter, so now we are going to have 1 mole per liter of A. So integrating, then we say that we will have the natural log of Ca0 divided by Ca equal to Kt, and taking logs, anti-logs of both sides, we will have Ca equals Ca0 times exponential to minus Kt, and the concentration of ethylene glycol at any time t can be obtained from the stoichiometry because A plus B gives us C, so Nc equal to Na0 times X, what is going to be formed, but Na0 times X is equal to Na0 minus Na, so then we will have that the concentration of C, which is Nc divided by B, but Nc is equal to Na0 minus Na. So at the end, we are going to have that C of C is equal to Ca0 minus Ca, and is going to be equal to Ca0 times 1 minus exponential to minus Kt, if we substitute the value of Ca that we just obtained before. Rearranging and taking the logarithm of both sides, we will have that natural log of Ca0 minus Cc divided by Ca0 equal to minus Kt. So we see that a plot of natural log of Ca0 minus Cc divided by Ca0 as a function of t will give us a straight line with a slope of k minus k, where k is the rate constant that we want to obtain. So using table A4/1.1, we can construct table A41 and use Excel. And using Excel, we are going to plot natural log of Ca0 minus Cc divided by Ca0 against t time. So we have here the values of t, and in the last column the values of natural log of Ca0 minus Cc divided by Ca0. And here we have the plot, and the slope, negative slope, is equal to minus 0.311 minus to the minus 1. That's the value of k. So the rate law becomes minus Ra equals 0.311 minus to the minus 1 Ca. The rate law can now be used in the design of an industrial CSTR.